Hello, welcome. In the previous week, we discussed vectors in Rn, vector spaces, subspaces of vector spaces, linear combinations, spanning sets, and linear independence and dependence, span of a set. In this part of the lecture, we are going to discuss about basis and dimension of a vector space, dimension of subspaces. Let's begin our discussion with the formal definition of a basis of a vector space. Definition: a set of vectors S containing the vectors v sub 1, v sub 2, all the way up to v sub n in a vector space V is called a basis for the vector space V if the following conditions hold true. 1. The set S spans the vector space V. 2. The set S is linearly independent. So condition 1 means that every vector V in the vector space V can be written as a linear combination of the vectors in the set S. And the condition 2 says the set S is linearly independent, meaning that no vector in the set S is a linear combination of the other vectors in the set S. This definition tells us that a basis has two features. It must have enough vectors to span the space. It should not have so many vectors that one of them could be written as a linear combination of the vectors in it. Example: we want to show that the set S containing these three vectors is a basis for the vector space R3. Let's have a look at the solution. In example 10.2.3 and 10.2.6, we proved that span of S is equal to the space R3, meaning that any vector in the vector space R3 can be written as a linear combination of vectors in the set S. And the set S is linearly independent. Thus, S is a basis for the vector space R3. This basis is called the standard basis for the vector space R3. Geometrically, we can think the first vector in this set S as the unit vector along the x-axis, which is usually written as I hat. Similarly, the second and the third vectors in the set S can be thought of the unit vectors along the y and z-axis, which are usually denoted as j hat and k hat. Similarly, the set S containing the vectors e sub 1, e sub 2, all the way up to e sub n, where e sub n is a vector with n components, with the first component is 1 and the rest of the components are zeros. Similarly, e sub 2 has the second component 1 and the rest of the components are zeros, and so on. The nth vector e sub n has the nth component equal to 1 and the rest of the components are zeros, is called the standard basis of the vector space Rn. In the next example, we want to show that the set S containing these three vectors from the vector space R3 is a basis for R3. In examples 10.2.4 and 10.2.7, we obtained that the set S spans the vector space R3 and S is linearly independent. Hence, S is a basis for the vector space R3. Example 11.1.1 and example 11.1.2 show that basis for a vector space is not unique. Let's have a look at another example. We want to show that the set S containing these four matrices is a basis for M sub 2, 2. Recall that M sub 2, 2 is a set of all 2 by 2 matrices with real entries. This is called the standard basis for the vector space M sub 2, 2. To show that S is a basis, we take an arbitrary matrix with entries A sub 1, 1, A sub 1, 2, A sub 2, 1, A sub 2, 2 from the vector space M sub 2, 2. Clearly, the matrix can be written as a linear combination of these four matrices in the set S. Therefore, the set spans the vector space M sub 2, 2. In other words, span of S is equal to M sub 2, 2. In order to complete the proof, we must show the set S is linearly independent. To show the linear independence, we solve the following vector equation for C sub 1, C sub 2, C sub 3, and C sub 4, where V sub 1 is the matrix 1, 0, 0, 1, and the matrices V sub 2, V sub 3, V sub 4 are as shown. So the left-hand side of the equation takes this form, and the right-hand side is replaced by the zero matrix in the vector space M sub 2, 2. The left-hand side of this matrix equation can be put into a single matrix, and the right-hand side stays as it is. Since these two matrices are equal, we must have C sub 1 is equal to 0, and C sub 2 is also equal to 0, and C sub 3 and C sub 4 are also equal to 0. So the equation we see here is only satisfied for this trivial solution. This shows that the set S is linearly independent. Thus, S is a basis for the vector space M sub 2, 2. Let's have a look at another example. We want to show that the set of these three polynomials, 1, x, and x squared, is a basis for the vector space P sub 2. Recall that P sub 2 is a set of all polynomials of this form: a sub 2 x squared plus a sub 1 x plus a sub 0, where a sub 2, a sub 1, and a sub 0 are real numbers. They can all be equal to 0. Let's denote v sub 1 equals to 1, v sub 2 equals to x, and v sub 3 equals to x squared. Now we take an arbitrary polynomial, a sub 2 x squared plus a sub 1 x plus a sub 0, from the vector space P sub 2. Then obviously the polynomial can be written as a sub 0 times v sub 1 plus a sub 2 times v sub 2 plus a sub 2 times v sub 3. Recall that v sub 1 is 1, v sub 2 is x, and v sub 3 is x squared. This shows that the span of S is equal to the vector space P sub 2, meaning that an arbitrary polynomial from the vector space P sub 2 can be written as a linear combination of these three vectors. For example, if we have a polynomial negative 2x squared plus 4x minus 5 from the vector space P sub 2, then it can also be written as negative 5 times v sub 1 plus 4 times v sub 2 plus negative 2 times v sub 3. Therefore, any polynomial from the vector space P sub 2 can be written as a linear combination of the vectors in the set S. Now, we will show the linear independence of the set S. To show that, we consider the defining equation of linear independence. C sub 1 v sub 1 plus C sub 2 v sub 2 plus C sub 3 v sub 3 equals to 0. If we can show that this equation has the only trivial solution, namely C sub 1 equals to C sub 2 equals to C sub 3 equals to 0, then we will claim the set S is linearly independent. To show that, we replace v sub 1 by 1, v sub 2 by x, and v sub 3 by x squared, and we obtain this equation. This equation is true for all value of x. So, by differentiating both sides with respect to x, we get c sub 2 plus 2 c sub 3 x equals to 0. Again, differentiating, we get 2 c sub 3 equals to 0. So this equation is also true for all value of x. So the last equation gives us c3 equals to 0. And if we substitute this value of c sub 3 into this equation, we get c sub 2 equals to 0. And then if we substitute the values of c sub 2 and c sub 3 into this equation, we get c sub 1 equals to 0. Hence, this equation has the only trivial solution. C sub 1 equals to C sub 2 equals to C sub 3 equals to 0. Thus, the set S of these three polynomials is linearly independent. Hence, S is a basis for the vector space P sub 2. In example 10.2.1, we observed that the vector v with these three components 1, 1, 1 in the vector space R3 can be written as a linear combination of vectors in the set S in various ways. For example, v is equal to v sub 1 minus v sub 2, or v equals to 2 v sub 1 minus 3 v sub 2 plus v sub 3. Let's check the first one. The next theorem tells us under what condition this representation is unique. Theorem: uniqueness of basis representation. If S be the set of the vectors v sub 1, v sub 2, all the way up to v sub n, is a basis for a vector space V, then every vector in V can be written in one and only one way as a linear combination of vectors in the set S. Let's try to prove this theorem. The existence portion of the proof is straightforward. Since S is a basis for the vector space V, S must span the vector space V. Thus, an arbitrary vector V in the vector space V can be expressed as shown in the equation 1. For some scalars c sub 1, c sub 2, all the way up to c sub n. To prove uniqueness, we assume V has another representation, as shown in equation 2. Let's assume that V can also be written as the linear combination of the vectors in S, as shown in equation 2, for some scalars d sub 1, d sub 2, all the way up to d sub n. We want to show that the corresponding coefficients in these two equations are equal, namely c sub 1 equals to d sub 1, c sub 2 equals to d sub 2, and all the way up to c sub n equals to d sub n. Thus, the uniqueness of the presentation will be proved. To show that, we subtract equation 2 from the equation 1, and we obtain this equation. Since S is linearly independent, so the only solution to this equation is the trivial solution, namely the coefficients are all equal to 0. Which means that c sub I equals to d sub I for all I, 1, 2, all the way up to n. And the vector V has only one presentation for the basis S. So we proved that a vector V in a vector space V can be written as a linear combination of the basis vectors in one and only one way. Theorem: if S is a set of n vectors, and if S is a basis for a vector space V, then every set containing more than n vectors in V is linearly dependent, hence cannot be a basis. So this theorem tells us that If a vector space has a basis of n vectors, then any other set containing more than n vectors in it must be linearly dependent, which cannot be a basis. To see the proof, please consult your textbook. Question: is the set S a basis for R3? Answer: no. Because in example 11.1.1, we found that one basis of R3 contains three vectors. Namely, the standard basis of R3 contains three vectors. Since this set S has four vectors in it, it must be linearly dependent. Hence, this set S is not a basis for the vector space R3. Corollary: if a vector space V has one basis with n vectors, then every basis for V has n vectors. In other words, if a basis for a vector space V has n vectors, then every other basis must have the same number of vectors, but not necessarily the same vectors. Let's see the proof. Let's take S sub 1, the set of vectors u sub 1, u sub 2, up to u sub m, and S sub 2, the set of vectors v sub 1, v sub 2, all the way up to v sub n, are two bases for the vector space V. We want to show that m equals to n, namely the number of vectors in the basis S1 is equal to the number of vectors in the basis S sub 2. Since S sub 1 is a basis, then by the theorem we proved just a moment ago, 11.1.2, S sub 2 cannot have more than m vectors. That is, n has to be smaller than or equal to m. By a similar argument, since S sub 2 is a basis, by the hypothesis, the set S sub 1 cannot have more than n vectors. That is, m has to be smaller than or equal to n. These two inequalities prove that m equals to n. The proof is complete. So we proved that if a basis for a vector space V has n vectors, then every other basis for the vector space V has the same number of vectors. Dimension of a vector space. Definition: if a vector space V has a basis consisting of n vectors, then the number n is called the dimension of the vector space V, and it is denoted by this symbol, which may be read as dimension of V. If V consists of the zero vector alone, the dimension of V is defined as 0. That is, if V is the vector space consisting of the zero vector only, then its dimension is defined to be equal to 0. In other words, if a vector space is spanned by a set of finitely many vectors of V, then it is called finite dimensional. Otherwise, it is called an infinite dimensional vector space. By using examples 11.1.1, 11.1.3, and 11.1.4, we can write the dimension of R3 space is equal to 3. Similarly, the dimension of the vector space M sub 2 comma 2 is 4. The dimension of P sub 2 equals to 3. Since its standard basis contains 3 elements. In general, the dimension of the vector space Rn is n. The dimension of M sub m comma n, which is the set of all m by n matrices over real numbers, is m times n. And the dimension of P sub n is equal to n plus 1. Some examples of finite dimensional vector spaces are Rn, Pn, m sub m comma n. On the other hand, C, the vector space of all continuous functions defined over the bounded and closed interval a to b, with a strictly smaller than b, is an example of an infinite dimensional vector space. Some other examples of infinite dimensional vector spaces are R infinity, P infinity. Please try to think about those spaces. Question: does every vector space have a basis? Yes. Unfortunately, it is beyond the scope of our discussion. Dimension of a subspace. In the next example, we will calculate the dimension of a subspace of a vector space. Find the dimension of the subspace W, which is a subspace of the vector space R3. Let's have a look at the solution. In example 10.1.1, we showed that W is a subspace of R3. To find its dimension, we take an arbitrary vector V from the space W with components x, 0, z. This vector can be written as shown here. X times the vector 1, 0, 0 plus z times the vector 0, 0, 1. This shows that any vector in the vector space W with components x, 0, z can be written as a linear combination of these two vectors. In other words, the span of the set S equals to the subspace W, where S is the set of these two vectors. Furthermore, the set S is linearly independent. To show this, we consider the following equation. The left-hand side of the equation takes this form when we replace v sub 1 and v sub 2 by the vectors with components 1, 0, 0 and 0, 0, 1. The right-hand side is the 0 vector in the vector space R3. The left-hand side of this equation can be written as a vector with components c sub 1, 0, c sub 2, which is equal to the 0 vector. This equation is true if and only if c sub 1 equals to c sub 2 equals to 0. Therefore, the set S is linearly independent. Hence, S is a basis for the subspace W. Since this basis has two vectors in it, therefore the dimension of W is 2. Let's have a look at another example. Find the dimension of the subspace S sub 2. That is the set of all 2 by 2 real symmetric matrices. The set S sub 2 is the set of all 2 by 2 matrices of this form. Recall that a matrix is symmetric if its transpose is equal to the matrix itself. We see that a matrix with these components is a symmetric matrix. To find the dimension of the subspace S sub 2, we take an arbitrary matrix A from the set S sub 2 with entries shown here, which can be written as a linear combination of these three matrices. Please verify. This shows that the set S with these three matrices spans the subspace S sub 2. To show that the set S is linearly independent, we consider the following equation, which, when replaced by the matrices as shown in the set S, takes this form. The left-hand side of this matrix equation becomes this matrix, and the right-hand side stays the same. Now, this equation is true if and only if c sub 1 equals to 0, c sub 2 equals to 0, c sub 3 equals to 0, and c sub 4 equals to 0. Since two matrices are equal if and only if the corresponding entries are equal. This proves S is linearly independent. Therefore, the set S is a basis for the subspace S sub 2. Thus, the dimension of S sub 2 is 3, since the set S has 3 elements in it. In other words, the vector space of all 2 by 2 symmetric matrices is a three-dimensional vector space. On the other hand, the vector space of all 2 by 2 matrices with real entries is a four-dimensional vector space. Theorem. Basis test in an n-dimensional space. Let V be a vector space of dimension n, and S is a set of n vectors in the vector space V. If any one of the following conditions hold, then we can claim S is a basis for the vector space V. Condition 1. If S is linearly independent, then S is a basis for V. Condition 2. If S spans V, then S is a basis for the vector space V. So this theorem tells us that if we have a vector space of dimension n, which we know in advance, then any set of n vectors would be a basis if any one of these two conditions hold. The proof of this theorem is given in the appendix of this note. Let's see an example. Show S is a basis for the vector space R3, where S contains these three vectors. In general, to show that a set S is a basis for a vector space, we need to check if S spans the vector space and S is linearly independent. In this case, since S contains three vectors and the dimension of the vector space R3 is 3, so we just need to check any one of the two conditions stated in the theorem 11.1.3. With this, we end the part 1 of this lecture. Thank you.